Ever pondered on how the cross product of two vectors is calculated? It's a fascinating operation in the realm of mathematics, producing a new vector from two others. So buckle up as we delve into the world of vectors. First, let's understand what this cross product really is. Picture two vectors, let's call them A and B. The cross product of these vectors produces a third vector, CE, that's perpendicular to both A and B. It's like the black sheep of the vector family, always standing at right angles to its parents. The magnitude or length of C mirrors the area of the parallelogram formed by A and B. Now, how do we get our hands on this elusive CE? Enter the formula. We calculate the cross product symbolized as a XB using the formula C equals I times the dot product of B and J minus J times the dot product of B and I plus K times the dot product of A and B. Here, I, J, and K are the unit vectors in the X, Y, and Z directions, respectively. Now that we have the formula, let's understand how to use it. To find the direction of the resultant vector, we use something called the right-hand rule. Here's how it works. Extend your right hand with your thumb pointing in the direction of the first vector. Next, curl your fingers towards the direction of the second vector. Now the direction your index finger is pointing, that's the direction of the cross product. It's a neat little trick that helps us visualize and understand the cross product better. Got your hand gestures right? Great, let's move on. The cross product isn't just about calculations, it has some fascinating properties. One of these is associativity. This means that if you take the cross product of three vectors, it doesn't matter where you put the parentheses, the result will be the same. That's AXBXC equals AXBXC. Another property is anti-commutativity, where the cross product of A and B is the negative of the cross product of B and A. That's AXB equals BXA. And here's an interesting one. The cross product of two vectors is zero only if the vectors are parallel. It's also worth noting that the resulting vector is always perpendicular to the original two vectors. These properties make the cross product a powerful tool in various fields. You might be wondering, where do we use this in real life? The cross product's applications are vast and varied, stretching across mathematics, physics, and engineering. It's instrumental in calculating torque, determining the area of a parallelogram, and even pinpointing the direction of a force. It plays a significant role in representing rotations in three-dimensional space, so the next time you see a rotating object, remember the cross product.